yesterday, my 8 o'clock class, about 45, 50 minutes into class, the computer restarted. So not only did the people in Zoom go, what the hell? The people in class, everything gone. So, oh, what's going on here? Oh, you're kidding me. Not again. Tyler?
What are you doing?
Yeah, I'm not doing so great because Zoom isn't behaving.
Oh man.
I got my camera on, but it's not showing up in Zoom. So either Zoom's not recognizing it or the there it is. Video. Start video. And it's blind. It shows that it's there. This camera. I'm going to try camera hanging from the ceiling. And it doesn't read the camera. That means I have to use my camera again. That's why I got to the classroom early to see if that was. Because I did bring my presentation camera, which is a much better camera than this one. So. But it's in my office. It's not with me. So this no page office.
But you want me to take down the sign outside?
What sign?
Says it'll be on Zoom today.
Oh. That's still up there. date. It'll click the date. Thank you for telling me. Problems with Zoom. Didn't have any problems with my English today. Yesterday I had problems in all three of my classes. And two of those classes were in the same classrooms. That's not the camera. Please put your name in the chat and please pin my screen. So up there at top, the title will be a little difficult to read right there, but most of the rest of it comes across okay. And the bright spot right here isn't too bad. Oh, okay. So, yeah, the signing is up front. Sorry. What do we have to send? We are at 12. Today was my oldest birthday. 40. So, go ahead. All right.
So guys,
Sealy,
I've got in class today. I know I'm one of those people. It's that class.
a number of people thought that
college has the same holidays as high school.
Oh, yeah.
It does not.
Have you guys never, ever celebrated Columbus Day or presently known as National Indigenous Peoples Day? Is that always a
The
thing?
college, at college level? No.
Yeah. Never, it was never celebrated.
No,
Oh, okay.
not even in state schools.
Oh,
Um, Labor Day,
Right.
yes. Martin Luther King Day,
yes.
yes. But that's it.
Okay.
Well, there's Thanksgiving weekend and Good Friday at Easter, but that doesn't affect classes.
Yeah.
because
Yeah, I was at freaking Chick-fil-A. Oh my God, looking at the time. Oh, no, I forgot.
All right, we're gonna be talking about the definition of identically equal, identity, and conditional equation. All right. Two functions are identically equal. If they equal each other. That means whatever I put in for X, I'll get the same thing for G. So if I put 7 here, I'll get the same thing if I put 7 here. If I put a negative 320 here, I'll get the same thing putting negative 320 here. So they get the same results, just a different pathway. Okay. Provided X is in the domain of both functions. Such an equation is also referred to as identity, because this is the same as that, so it's just looking at a mirror. Kind of. But it's called identity because you get the same number on both sides. 5 plus 3 and 8 are equal. So that's identity. 5 plus 8 is the same as 4 plus 4. They're identically equal, and that equation is identity. Okay. Because 8 equals 8. And then any equation that is not identity or identically equal, then it's called a conditional equation. Most equations we've dealt with are that type. 3x plus 2 equals 4. It all depends upon what we put in for x to make it a true statement. Like quadratic equations are conditional because they're only true if you put the right numbers in for x. All right, the quotient identities we already know, or you should already know. The reciprocal identities you should know. Because I keep harping on them. And Pythagorean identities, please realize that the Pythagorean identities are not always used this same way every time. Okay. Sometimes you might have something that says, well, you have 1 minus sine squared theta. Well, if I subtract sine squared from both sides here, then cosine is going to equal 1 minus sine squared. So this is a true statement. So this is also part of the Pythagorean identities, because we can change those equations around to get another equation that are still equal. So this is equivalent to that Pythagorean identity. Equivalent is another one of those fancy words. That means it's equal, or it's saying the same thing. Anyway, whatever you put in for theta, you're going to get the same result. And then the even odd nature of sine, cosecant, tangent, and cotangent, the odd properties of those four. This is very useful. And same thing with cosine. Cosine and secant are even functions. So the cosine of a negative is the cosine of the positive. Same thing with secant. Cosine of the positive is the same as the cosine of the negative. Now, we're going to be using these identities and other algebraic techniques to establish identities. What they mean by establishing identities is to show that this side does in fact equal that side. So I'm going to change one side so it looks like the other side. Rewriting a trig expression in terms of sine and cosine only. That is sometimes useful in establishing the identity. Multiplying the numerator and denominator by a ratio, by a well-chosen one. Right? I always say we're multiplying by one. It just depends on what one looks like. Sine over sine, cosine over cosine. So we're always multiplying by one. It just, what is that one going to look like? When you first started adding and subtracting fractions, that's exactly what you were doing. You were multiplying by one. So you changed what it looked like, not what it is. And then writing sums of trig ratios as a single ratio. And to do this, you're going to come back to this. So to do number 3, you have to do number 2. Or you factor and reduce. Sometimes that does. And then factoring. And so that's what I was talking about there, is factoring, so that it simplifies the expression, it gets rid of terms. Because they go to 1, you can factor out your 1s. Okay. That's tangent theta in the numerator. You can simplify. Okay. Now, so rewriting that as sine over cosine divided by 1 over cosine.
So we're left with sine.
Yeah, that would equal sine. Dividing by secant is the same as multiplying by cosine. So sine over cosine times cosine is sine. Well, the slide works them out, so. This. Show that those are equal simply by multiplying the denominator here and the numerator by 1 plus cosine theta. So we're going to multiply by 1. And the one we're going to multiply by is 1 plus cosine divided by 1 plus cosine of theta. Okay, so this is what we're going to multiply this fraction by. To show that those two things are equal. And it works out quite nice. It's kind of a fun little thing that happens. And we factor here. All right, notice we have the difference of two squares. Cosine squared and 1 is 1 squared. And so you can factor this to cosine minus 1 and cosine plus 1. And then we can factor tangent out of the denominators here. And so we can see what happens. All right, then rewriting this as a single fraction, a single ratio, this fraction I'm going to multiply by 1, which is cosine over cosine. And this one I'm going to multiply by 1, which is sine over sine. So my denominators are the same. And then I simplify. So here they rewrote it as sine over cosine divided by cosine. Oh, I mean 1 over cosine, 1 over cosine, dividing by 1 over cosine is the same as multiplying by cosine over 1. So the cosines go bye-bye. Because that cosine over cosine is 1, so I'm taking out our 1s. And it leaves us with sine. So tangent over secant equals sine. Okay. Convenience stores close to do not have zero one.
Which is Bang? Oh, Mega Bang?
Yeah.
Oh, you like the zero sugar one?
Prefer the high octane full baked bread, but I'm diabetic, so. So here, they want you to multiply numerator and denominator by 1 plus cosine. So here I'm multiplying by a sum and a difference of the two same numbers, two same terms. So this, when you multiply a difference and a sum together, you of the same two terms, then you get the difference of two squares, perfect squares. So 1 squared minus cosine squared in the denominator. And I'm going to leave sine, I'm going to leave the numerator as sine times 1 plus cosine. We don't. Now we use a trig identity to change this. 1 minus cosine squared. What does that equal? There's a reason why when we got the slide about the Pythagorean triplets, why I focused on that.
It's
What's the first what's the first Pythagorean
Sine
identity?
squared theta plus cosine squared theta equals 1.
All right, so I'm
So
going to
that
get
equals
it, so
1.
one side is 1 minus cosine
Yeah.
squared. So what's the other side?
You talking about the numerator side?
No, I'm talking about that identity.
Oh. It's sine.
Sine
squared.
is sine squared.
Yeah.
So down here becomes sine squared. Well, one of these signs down here goes away with that sign. And
And
I
then
like
it's sine over
I
sine.
like to do that. So now it's just 1 plus cosine over sine. Or cosecant plus cotangent. Oh, they don't do that.
I was good. Yeah, no, it's
They left it as a single fraction. So, oh, that's what they wanted Yeah, wasn't it? No, they just wanted to know what happens when you multiply numerator and denominator by that fraction. By, yeah. Now, letter C here, they want us to factor. Well, it's similar to this one, where we were multiplying a sum and a difference to get the difference of two squares. Now we have the difference of two squares, and I can rewrite it as,
Cosine theta minus one.
and,
We factored out the tangent.
what?
Didn't you say a factor?
Yeah, you factor the numerator.
Uh-huh. Okay, so then cosine theta minus one over tangent squared.
No,
No?
I'm just looking at factoring the numerator. I don't know what you're doing.
Okay.
Just
So-
factor the numerator.
Oh, then sine,
Nope.
because aren't we left with cosine theta minus one? Also tangent.
1 minus cosine is sine squared. 1 minus cosine squared is sine squared. But cosine squared minus 1, that's not the same. So we want to factor this. I have the difference of two squares. The difference of two squares factors quite nicely. A squared minus B squared equals A minus B times A plus B. Here I have the sum and difference of the same two terms. When I multiply the product of the sum and difference of the same two terms is the difference of two squares. The factor of the difference of two squares is the product of the sum and difference of the two square roots. So factor the numerator. What's the square root of cosine squared?
Cosine,
Cosine.
Yeah.
What's the square root of 1?
one.
So A is cosine, B is 1. A is cosine, B is 1.
Plus.
And then in the denominator, we're just going
Oh.
to factor the tangent out. You do them separate.
Yeah, no, I was canceling.
No, you can't do that.
Yeah, that's what I was doing.
You can't do that.
Okay.
I
That's what I was
can't,
getting
I
at.
can't take this out with one of these.
Yeah.
No,
No.
because this is one thing.
Okay.
I have to do the entire thing, not just part of it.
Yeah, that's where I was.
Now I have I have a factor here and a factor here that are the same, so those can go away. Right, because when I factor tangent out of here, this goes to just cosine, and tangent divided by tangent is 1. The biggest mistake I've seen students do is when they factor something out of itself, it disappears. It doesn't disappear, it becomes 1 because you're dividing it by itself. And so those two go to 1, and it will leave us with cosine theta minus 1 divided by tangent. And there it is simplified. Yeah. Oh. This is a case of getting the denominators the same. So to get the denominator the same, I'm going to have to multiply the numerator and denominator here by cosine, and the numerator and denominator here by sine, so they're both sine cosine. Sine u times cosine. So I'm going to multiply the numerator of the first fraction by cosine. And this is a case of where you actually do the multiply because we're going to have to add our numerators.
So
our
we're gonna-
denominators become the same, so we can write it as one single fraction. Sine u cosine u is the denominator. And cosine u times 1, cosine u times sine, sine u times cotangent, and sine u times cosine.
Can we just get rid of sine u, cosine u by canceling at this point?
You're subtracting something that you put in. They added 0, so they're gonna take the 0 out.
Yeah.
Now I can change this.
Yep.
But, well, what do they do here? Let me see. Oh, I know. Cotangent is cosine over sine. Yep. Boom. Well, now what happens here?
You gotta multiply by sine,
No, what happens here?
those cancel,
Well, they don't cancel,
you get rid of them.
they go to 1. So this is sine over sine. So that's 1, so those go away. They didn't do their
So you're
nice
left
little
with-
line through there.
So you're left with cosine plus cosine,
What's cosine plus cosine?
2 cosine.
2 cosine. So the numerator becomes 2 cosine. And what do you know? We have a factor in the numerator and a factor in the denominator that is the same. Right? This is 2 times cosine. And this is sine times cosine.
So we're left with cosine over sine.
How'd you get cosine in the numerator left? What happens here? What's cosine over cosine?
Oh, then we got 2 of them?
Well, that's 2 times cosine.
Okay. So we're left with 2 over sine,
Right?
okay. All right, I'll keep that.
Because you're thinking squared.
Yeah,
This-
That's not
this is
squared.
it. Squared means you have 2 cosines that are being multiplied. This just means there's one cosine being multiplied
By
by
2.
2. And so this is a factor, this is a factor, they're the same, so they equal 1. Okay. I mean, you're using algebra, basic algebra facts,
Mhm.
as well as the trig identities thrown in for good measure. And then it's just a matter of looking at the puzzle, what other pieces can I bring in to help change this thing so I can make it look different? So we're gonna establish this identity. Cosecant times tangent equals secant.
1 over sine. 1 over cotangent equals 1 over cosine. We're not gonna use our reciprocal identities.
For one of them, we're gonna do 2 things. This side is more complicated, so we want to make this one end up looking like this one. We're not gonna do anything to this side. All we're gonna do, we're gonna change this side till it looks like this. Yeah, cosecant, so I want to write everything as sine and cosine. All right, cosecant is 1 over sine, tangent is sine over cosine. So what happens to those sines?
They turn into 1.
They go to 1, so they disappear. So now I just 1 over cosine. What is 1 over cosine?
Secant.
Secant. Boom. That was an easy one. This is from my point of view, this is the fun stuff. Okay. So the right side has been reached, so the identity is established. Sine squared of negative theta plus cosine squared of negative theta equals 1. How is that the Pythagorean identity?
first we have to, our even odd identities, we have to make them,
Well, before you do that, you need to be very careful here.
okay,
Because you're squaring sine. You're squaring sine, so I'm gonna square sine of negative theta. I'm squaring cosine, which is I'm squaring the cosine of negative theta. So I rewrote it to show exactly what's going on with the square. Now we bring in the even odd.
and it comes out being the same.
Yeah, because this becomes out sine, I'm gonna square the negative of sine theta. Because the sine of negative theta is the negative of sine theta, and I'm squaring it.
Yeah.
And then cosine
That
of
makes
negative
sense.
theta is just cosine of theta.
Yep.
Well, when you square a negative, what do you get?
Positive.
A positive.
Yeah, that's what I was gonna say, yeah, they just end up being.
So then this is just the same as sine squared plus cosine squared, which is exactly what it is. Sine squared theta. This means the exact same thing as sine squared theta. You're going to take the sine of theta and square it. And take the cosine of theta and square it. And then add them together, you get 1.
Cool.
Because the natural inclination here is just to bring this negative sign out here.
Yeah, that's what I was,
Well, that's not taking into account that you're squaring it.
right,
Because once you square it, it becomes positive.
Mhm.
So sine squared of negative theta is the same thing as sine squared of theta.
Awesome.
Establishing this sign that this is cosine.
well, now we know because of our last problem that the numerator is 1.
No. Oh, the numerator?
Yeah. The top of the fraction is 1. Because of what we just did. Oh.
It's not plus, it's minus. So that changes things.
Changes. So close.
Well, I'm going to change both
By
the
squaring,
numerator and denominator first by rewriting the numerator. And then we're going to use the even odd nature of sine and cosine.
which makes our cosine negative.
Well,
And it turns it into.
it's going to stay minus cosine squared theta. This is going to stay minus cosine theta. And this is going to be a negative sine of theta. So the top part mimics what happened in the previous problem, except we're going to have a minus sign here instead of a plus sign because that's what the problem is. Now, sine of negative theta is the negative sine of theta. That minus sign stays there. And now when I square this, I get cosine, I get sine squared minus cosine being squared. And in my denominator, can't I factor out a -1?
Yes.
So that's something you need to be thinking about. What if I factor out a negative? Does it change it enough to look like what's going on in the numerator? But we're not there yet. Because now we want to factor this. I have something squared minus something squared, so now I have the difference of 2 squares. We use this all the time.
High school stuff.
Okay.
Sine theta plus cosine, and then sine theta minus cosine.
Right. So this would be sine theta minus cosine theta. And this would be sine theta plus cosine theta.
And then once we factor out from the denominator, we can cancel one.
-1, right? And that's what they did. They went ahead and factored out the -1.
So we can cancel,
And yeah, not cancel,
or turn into one.
turn to 1. Because we're still multiplying by a -1. So the -1 makes this negative.
Which turns it positive, which equals one.
No. The sign becomes minus, the
And now-
cosine becomes plus, and we typically write the positive first, which is why they wrote it this way.
That doesn't equal.
Because what you have there, you have sine theta minus cosine theta divided by a -1, which is the same as multiplying by -1. Which is a negative sine theta plus cosine theta, which they rewrite this way.
Mm.
And that's how but if you leave it this way on the test, I don't care. This is good.
Isn't it, what do they call it, sir? They teach you in algebra, of descending order? Is that what that?
No,
be?
you're just using commutative property, so the positive first. That's all. And mathematicians like, if you have
Yeah,
if you're
isn't that-
combining a negative and a positive, you write the positive minus.
Isn't that in descending order or something?
No.
No?
No.
I don't even know if I'm using the right term. It's kind of like,
Yeah, you're talking about polynomials.
there you go.
We always write them in descending order. And descending order deals with the exponents
More than,
on the variable.
okay,
The variable in this case is theta,
yeah, so it's the same.
so it's not. Yeah. I'm trying to remember how they deal with this one.
Sine
1
over
plus
cosine.
tangent u over 1 plus use the quotient identity. I think, yeah.
Or
Oh,
just
they
divide?
use the inverse identity here. So now they're gonna write, because I can write this being tangent, so everything is in tangent.
Instead of
And
having the trouble of being cosine,
because we
sine.
need to get tangent in our answer.
Instead of having sine, cosine, cosine, sine.
Right, then it gets messy.
Okay.
It can be done, but it gets messy. And so writing this as a single fraction, and this is the same as 1 plus tangent u divided by 1 times tangent u divided by
And
tangent u plus 1. 1 plus tangent is the same as tangent plus 1. That's just the commutative property. And hopefully you can see that's just going to give us tangent. Okay. So yeah, so they did that. So this is this fraction here.
sure.
Right, yeah. This part,
Yeah, it's the bottom of, is the.
if you ignore this right here.
Oh, yeah.
You have this fraction, and I'm just multiplying it by this.
Yep.
Well, it's like if I put this in front here, I get the same thing. And then the tangent, the 1 plus tangent, or the tangent plus 1, they go to 1. And so that just leaves tangent. So 1 plus tangent over 1 plus cotangent equals tangent. Well,
Okay, so when we got 1 plus 1 over tangent, we multiply both sides by tangent. In the denominator,
how? What?
I'm just trying to figure out how we got from 1 plus 1 over tangent to tangent plus 1 over tangent at the top.
Up here?
Yeah, how did we
All
get
right.
that denominator?
Because this one here, I write as tangent u over tangent u, because I want to write it as a single fraction. So with the denominator being the same, all the action happens in the numerator. And it's over the common denominator.
Yeah. Oh, okay. Okay,
So that's how they got this
so we multiply.
this denominator. And then when you're dividing by a fraction, it's the same as multiplying by its reciprocal. I used to explain why that's so.
Is that an equal sign for the 2 cosecant theta, or is that?
Yeah. This is an equal sign, and this is 2 cosecant.
Okay,
So
one
I
equals-
want to write it as a single fraction to see what can happen. So I'm going to multiply numerator and denominator here by sign. And I'm going to multiply numerator and denominator over here by 1 plus cosine. Yeah, the left side is much more common. Okay. They don't show how that happens, but that's what you get, because I'm going to multiply this denominator and this numerator by sine over sine. And then I'm going to multiply this numerator
1 plus cosine
in this, right, by 1 plus cosine.
theta.
So the two fractions will have the same denominator. And they put the 1 plus cosine first. That doesn't matter. And in this case, we're going to multiply that out.
1 plus cosine theta, 1 minus cosine.
No,
Oh, not the difference? Oh, is that a difference?
no, you're multiplying. You're multiplying this by itself. That's what the square means. I'm going to multiply this binomial by this binomial.
Okay. Yeah.
So now your numerator becomes sine squared theta plus 1 plus 2 cosine theta plus cosine squared theta. All divided by 1 plus cosine theta times sine theta. Now, we don't multiply the denominator out because we want to see if things will factor nicely. Because I want to see if we're going to be left with something that I can reduce to 2 times cosecant. What happens here?
That equals 1.
Right? Because now you have sine theta, sine squared plus cosine squared, which is 1. So now this is going to be, these come out as 1 plus 1 is 2 plus 2 cosine theta divided by 1 plus cosine theta times sine theta. Well, that looks like a T there, doesn't it? Okay. I can factor 2 out of both of these.
We didn't have when at the top of the numerator, sine theta sine squared theta. Where did you get that extra one in front of the 2 cosine theta?
Because what's cosine plus
No,
sine
yeah, I
squared
get
plus
that
cosine
one.
squared is 1.
Right.
We already had a plus 1
Where did
here.
that one come?
Here. Because by multiplying these two together,
You get 2 cosine.
1 times 1 is 1,
Oh, we're multiplying.
and then 1 times cosine is cosine,
Yeah.
and cosine times 1 is cosine, and you add them to
1
get
plus
2
2
cosine
cosine
theta.
theta. Yeah,
And then cosine times cosine is cosine squared.
that's a polynomial, yeah,
So you get a quadratic.
yes.
And so we're gonna add 1 and 1.
Okay.
And this is the 1. That's where that 1 came from.
Yeah, I remember that.
So now I have 2 times 1 plus cosine theta divided by 1 plus cosine theta times sine theta.
So we turn those into 1.
The 1 plus cosine and the 1 plus cosine go to 1. So now this is just 2 over sine, which is what? What's our target?
2 cosecant theta, so then.
So what's over 1 over cosine? I mean 1 over sine.
Cosecant,
So 2 over sine is
2 cosecant.
they do the same thing. They don't show some of the steps, and they're not quite as messy as I am. Yeah, they didn't show multiplying here. And then, yeah, they're here. This here is the same as what I got. And then the sine squared plus the cosine squared gives us. Oh, they did the commutative property by putting cosine squared next to sine squared to show that that's going to be. Well, they didn't show that it becomes 1 plus 1 plus cosine, which gives us 2 plus 2 cosine. Oh, they show this here, this fact here to get the 1, and then adding to the 1 that was already there. And then factoring out the 2, and then whoever wrote this here in this PowerPoint, I want to smack them. Okay. Reciprocal identity. We really want to get technical about this. This is going to be 2 times 1 over sine, which is 2 times cosine. But no, we don't do that. All right. Showing that tan B plus cotangent B divided by cosecant B secant B times cosecant B is 1. Right. I would write this as 2 separate fractions, but maybe not. Write everything in terms of sine and cosine? Yeah. So the common denominator here is going to be sine times, because what happens, I don't know what they do next. Let me see what they do. I don't want to jump to that right away. Yeah. Yeah, I like it. They do what I would do. Multiplying everything so you get the same denominator, which is cosine times sine. So I'm going to multiply by sine over sine and cosine over cosine. So my denominator in the numerator is going to be cosine V, sine V. And I have sine squared because I multiplied by sine here. And then cosine squared because I multiplied by cosine here. And my denominator is just 1 over cosine sine. Well, at this point, I have it in my hand, damn it. At this point, I would say that since the denominators of the two fractions are the same, that would go to 1. But I think they attack it a little differently. And what's sine squared plus cosine squared? What's sine squared plus cosine squared?
2.
What's sine squared plus cosine squared?
I don't wanna do it.
Do it.
Is it?
Sine squared b plus cosine squared b. What does that equal?
2.
Is it one?
It's a Pythagorean identity.
Yeah, so 1.
1.
But what was missing the answer was the squared. Oh no, but the Pythagorean identity.
It has squares.
Okay, so then 1, yeah. I was debating between 2 and 1. So 1.
Okay. So this is 1 over 1 divided by 1 over 1,
Which is 1.
which is what?
Which is what we were trying to.
Which was what our A was. So they're saying this is 1 over cosine sine. And so I'm dividing 1 over cosine sine by 1 over cosine sine. I'm dividing a number by itself, so that's 1. But they turned this into a reciprocal and multiply, and the cosine signs go away, and that's just 1 over 1, which is 1. There's so many pathways on this particular problem. But working just from here, getting a 1 up here means you're having the same fraction in the numerator and denominator. That just equals 1. So I don't even see the need for the last step that they put in there. But anyway.
Over sine. We do not, or no, we make them equal. We make them the same denominator. Is that a minus or an equal?
That's an equals.
Oh, okay.
So I want to make one fraction look like the other fraction. Start with the left side, multiplying the numerator and denominator by this, because I want to put this in the denominator. To put this in the denominator means I have to multiply the numerator and denominator by the same thing. Alternatively, we could have done the same thing over here. But I would have multiplied by cosine. Ah, yeah, I see how that works. No, I would multiply by 1 minus sine. I'd multiply by cosine. Numerator and denominator by cosine, because I want to put cosine in the denominator. Oh, I see how that would work. Yeah, that would work. Because the way they would do it, you would, one would come out. So the cosine would disappear from the numerator and you end up with cosine in the denominator. But, oh, and that's what they did. They multiply that by one. I think that's a more complicated way of doing it, but we can do that. So my denominator is just cosine times 1 plus sine. But in the numerator, I'm multiplying a sum and a difference of the same two factors, I mean the same two terms. So I'm going to get the difference of two squares. So I'm going to get 1 minus sine squared in the numerator. Well, what is 1 minus sine squared?
0.
Nope.
Oh,
What
the
is
difference in two squares, 1 plus sine, 1 minus sine.
Well, that's how we got this. I don't want to factor again.
Oh, yeah.
What trig identity is this? What's the trig identity we've been using the most often this afternoon?
The Pythagorean identity.
Right,
So that's cosine.
that's cosine squared.
Yeah.
So now my numerator is cosine squared. Don't I have a cosine as a factor in the numerator and in the denominator?
Yes, sir.
So we cross those out. And what are we left with?
Cosine over 1 plus. And then,
So that's the other side.
so then 1 minus sine theta over cosine equals cosine
Huh?
over 1 plus sine theta. Because we just worked out the right side, didn't we?
Yeah, we attacked the left-hand side.
Oh. Oh.
And this is what the right-hand side looks like.
Oh.
If we started out the other way, then if I multiply numerator and denominator here by 1 minus cosine, so my numerator, I would have cosine theta times 1 minus sine theta. But my denominator becomes 1 minus sine squared theta, which is cosine squared theta. And so this cosine, one of those cosine goes away with that. And this equals this. So then we have 1 minus sine theta over cosine theta, which is what we started with here. So it's just doing the same thing. It's just the manipulations are obvious. It is almost always preferable, to start with the side containing the more complicated expression. Rewrite sums or differences of quotients as a single quotient. So you write fractions as a single, adding and subtracting fractions, you write them as a single fraction. Sometimes it helps to rewrite one side in terms of sine and cosine only. And you always keep the goal in mind. At one point, I kind of lost it that we were trying to equal it to tangent. And so I was kind of going in a different direction in my head. Until I realized we're trying to get to tangent. But I worked one time where you went far afield before you started coming to your actual goal. So it's weird. That happens sometimes. As you manipulate one side of the expression, keep in mind the form of the expression on the other side. So like that one where you have 2 cosecant theta, you need to realize that you could wind up with 2 over sine to get that 2 cosecant. Sum and difference formulas. Oh, yeah. This is where things get really interesting. Use sum and difference formulas to find exact values. Use sum and difference formulas to establish identities. Use sum and difference formulas involving inverse trig functions and solve trig equations linear in sine and cosine.
To use sum and difference formula.
What?
Okay. It's just funny, it was use sum and difference formula, use sum and difference formula.
Yeah.
Sine and cosine.
Okay. So you get trigonometric equations that are linear in sine and cosine. And solving those things. These are the sum and difference formulas for cosine and sine. No, for cosine. This comes in handy, especially if you can write a single angle as the addition or the sum of 2 angles you know the sine and cosine. So like 75. 75 is 45 plus 30. So I can use cosine. I can use the sum, cosine of the sum of 2 angles to find out exactly what that equals. Now, cosine of the sum is the difference of these 2 products. So the sum of the 2 angles gives you a difference of the products, where the difference of the angles, like suppose I wanted to get the cosine of 15 degrees. Well, 45 minus 30 is 15. And I know the cosine and sine of 45 and the cosine and sine of 30. But the difference of the 2 angles is the sum of the 2 products. Another way of writing it, which is the way I was taught it, which used to confuse the hell out of me, but cosine of alpha plus or minus beta equals the cosine alpha times the cosine beta minus or plus the sine of alpha, the sine of beta. Oh, that little thing got moved. No, not that. The left part. Left part. There you go. Okay, we have plus or minus here, but minus or plus here because the plus goes with the minus goes with the plus. Cosine is x. So you have a sign change there. So but once I got straight that if it's plus here, it's minus here, and it's minus here, then it's plus here. This one, I see this one as the easy. Sine is a little more complicated. There it is. So now, we have this. Find the exact value of the cosine of 105. 105, well, isn't that 45 plus 60?
Busting out our TIs for this, sir?
No, because they want, see when it says here,
Yeah.
exact?
Yes,
Don't
Oh,
use-
exact value.
Yeah, you don't use TI for exact values,
okay.
because you're gonna have square roots here,
Mhm.
and TI won't do that for you. So now we have the cosine of 45 plus 60. So it's gonna be the cosine of 45 times the cosine of 60 minus, because it's plus here, then it's gonna be minus the sine of 45 times the sine of 60. Okay. Cosine of 45, what is that? Cosine of 45 and the sine of 45 are the exact same number. Think of those x and y values on the unit circle.
Yes, 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 yes.
This is the x value for 45 and this is the y value for 45. They happen to be the exact same number. Which is what?
I don't have.
That's why you need, the first quadrant is the key.
Yeah.
Memorize the first quadrant.
Pi over, you looking for pies?
No,
No.
45 is pi over 4.
Square root of, oh, square root of, two times the square root of 3 over 2 is sine. No. Is it-
That's either secant or cosecant. I don't know.
It's square, 2 times the square root of 3 over 2.
No,
No.
unit circle.
I fleshed it out by memory with the patterns. I remembered you have the 3 that are the same here, and then they flip on the bottom.
Yeah, but this is the only ones you need to remember.
Yeah, because off of that one you can.
You can build all the others, all
Yeah.
of these,
And I knew it during the.
because then you have this relationship with all
Yes.
the 45-degree angles.
Exactly, and you started off with the 3 over 2.
No.
2 over 2, square root of 2 over 2, and then square root of 2 over 2, minus the square root of 2 over 2.
Square root of 2 over 2 and the square root of 2 over 2. In this quadrant, everything is positive.
Yep.
So 60 degrees is here. What are those x and y values?
3 times the square root of 2 over 2.
Nope.
Oh. Isn't it just square root of 3 over 2 then?
Yeah, but which one? Is that the x or the y?
That's the.
And what's the other one?
The other one's 1/2.
So which is which?
The x is 1/2.
Exactly.
And then the other one
So
is square root of 3 over 2.
this is 1/2, and this is the square root of 2 over 2. Cosine and sine of 45 or pi over 4 are the same thing. But what's the cosine of 60? That's the y value here.
Yeah, so the y value is square root of 3 over 2.
Right.
And then on the bottom,
And
it
for
flips.
60, yeah, it switched. It's square root of 2 over square root of 3 over 2 and 1/2.
And now you just go, you can go around with those
So
3.
then it's just these same 3. ordered pairs, it's just which one's negative, which one's positive.
Yep.
And so, yeah, so this is gonna be square root of 3 over 2. And so that's what they do, they convert it to that product. So you have 1/2 times, square root of 2 over 2 times 1/2, and the square root of 2 over 2 times the square root of 3 over 2. Multiplying here, you get the square root of 2 over 4, right? Because you just multiply the denominators and multiply the numerators. Because the square root symbol is over the 2, you can't reduce any of the 2's out of this. And when you're multiplying radicals, as long as the index is the same, you can multiply what's under the radical together. So 2 square root of 2 times the square root of 3 is the same as the square root of 2 times 3, which is the square root of 6. And so you get, I hate it that they do this. So you get this. And they factor the 1/4 to the outside. I don't. I write it as a single fraction. So, and I don't know how my math lab wants you to do it. So I would write this as the square root of 2 over 4 minus the square root of 6 over 4, which is the square root of 2 minus the square root of 6 divided by 4. But what they do, they factor the 1/4 out. You know, on the test, how you write it, if you write it this way or you write it this way, I don't care. Because they're both the same number. The way I view it, this is a fraction, where this is a fraction times a number. Semantically, they're different. One's a single number, and the other's a product. So now we want to find, all right, I did this one different than the way they did it. But that's fine. I want 2 factors of 12, and they don't have to be pairs like 3 times 4 or 6 times 2. Any factor of 12 and subtract another factor of 12, or add them to get 5. Oh, this one they do the same.
You get 6.
So 3 and 2 and 3, right?
Yep.
2 plus 3. So I can rewrite 5 pi as 2 pi plus 3 pi. Right? 2 pi plus 3 pi, and then I can split it into 2 separate fractions. Right? What the step they're missing in here in the middle is 2 pi plus 3 pi divided by 12, which I can write as 2 separate fractions with the same denominator. Well, 2 over 12, that reduces. And 3 over 12, that reduces. So 2 pi over 12 is the same as what?
Oh.
Pi over 6.
Pi over 6. I think someone said it. And then 3 pi over 12 reduces to what?
1 over 6. Pi over 6.
No. Pi over 4. Right? 3 over 12?
Pi over.
Yeah, 3 times 1 is 3. 3 times 4 is 12. So the 3's go away, leaves us 1 over 12. So that's pi over 12. So now I'm gonna use the sum formula. Because I'm adding the two angles, that means I'm gonna subtract the two products. So it's cosine of pi over 6 times the cosine of pi over 4 minus the sine of pi over 6 times the sine of pi over 4. Well, we know the cosine of pi over 4 and the sine of pi over 4 are the same number.
Yes.
And this is the cosine of pi over 6 is the same as the cosine of 60. I mean,
No,
30.
30.
30. And so this would be like the sine of 30. So what is the x value for pi over 6?
1.5. 1.5, because earlier we said 60, we said that the x value was 1.5. So for 30, the y value is 1.5.
Yeah, so I was asking for the cosine.
1.5.
No,
Oh,
the cosine of 60 is 1/2. So the cosine of 30 won't be the same.
square root of 3 over 2.
All right, square root of 3 over 2.
Cosine goes first and sine goes second.
All right,
Ugh,
this is the x value, this is the y value.
ugh. Ugh.
And so we have the square root of 3 over 2 times the square root of 2 over 2. And we have 1/2 times the square root of 2 over 2, and we're subtracting those two products. So we get a similar answer as the previous problem, except it's going to be the square root of 6 minus 2 divided by 4. And they factored the 1/4 to the outside. So it looks very similar to the previous answer, except the other one was square root of 2 minus 6. And these are identities. All right, sine and cosine are 1/2 a pi apart. So 1 minus theta gives us sine. Oh, yeah, that's it. Oh, don't do that. It's okay. I've done it before. Okay, so cosine of pi over 2 minus theta using the cosine formula. So we're going to get cosine of pi over 2 times the cosine of theta plus, because if it's minus, we're going to add the products, plus the sine of pi over 2 times the sine of theta. Well, what's the cosine of 1/2? 1/2 theta? I mean, 1/2 pi?
0.
0. So 0 times cosine,
0.
so this goes away. So we're left with this over here. What's sine of 90?
1.
1. 1 times sine theta. Boom.
Boom.
Now we haven't covered the sine formulas for adding and subtracting angles, but it works out in a similar manner here, where you're multiplying one of the two products by 0, and the other one gets multiplied by 1, and you wind up with cosine. Ow. So here are the formulas for sine. They're very similar, but very different than the cosine. The first difference to notice is that if you're adding the two angles, you're adding the two products. And if you're subtracting the two angles, you're subtracting the two products. The two products remain the same for both formulas. Okay. With sine, it's going to be sine times sine of alpha times cosine of beta, and cosine of alpha times the sine of beta. Or alternatively, no, they keep changing these formulas every now and again, because how I learned it is slightly different. Was sine alpha cosine beta plus sine beta times cosine alpha. So the way that I learned it, they kept the sine and cosine in the same place and moved the alpha and beta. Here they're keeping the alpha and beta in the same place and moving the sine and cosine. And you get the same thing. It's just using the commutative property with multiplication here. But for some reason in my head, this is taking over. Mainly because I teach it all the time. But so I can write this as a single, I can write the two equations as one using plus or minus. It's going to be sine of alpha plus or minus beta equals sine of alpha cosine of beta. Plus or minus is the same order. If it's plus here, it's going to be plus here. If it's minus here, it's minus here. Cosine beta times sine. No, cosine alpha. Sine beta. I got thrown backwards there for a second. And this is how they gave it to us when I in the class I took. I don't remember what class that was, but they showed it as a single equation with the plus or minus symbols. I think that's one reason I had a hard time with it. They'd had 13 years of teaching it to put it in my head. Okay. Oh. Now we want pi over 12. Pi over 12. Well, again, I'm going to look at factors of 12 that when I subtract gives me 1.
3, 4.
3 and 4, 2 and 3.
12 and 1.
12 and 1 do not subtract to 1.
I think you went for it, so that's impulsive.
I could use 1 and 2, but I don't know what the sign of pi over 12 is. So I did what you did. I said 4 pi minus 3 pi over 12 is the same as pi over 12. So we have 4 pi. No, we have 4 pi over 12 minus 3 pi over 12, which gives us pi over 3 minus pi over 4. So I'm gonna go ahead and do this one up here, and then we'll see what they do. So now we have the sine of pi over 4 minus pi over 3, which is the sine of pi over 4 times the cosine of pi over 3. And since we're subtracting here, we're going to subtract the products. And then it's going to be the cosine of pi over 4 times the sine of pi over 3. We're losing people in Zoom. What's happening?
Not sure. Wait, how many did we start off with?
5, 6, including me.
Huh.
Yeah.
So we lost 2 people.
Who's lost 3 people?
There's currently 4, including you.
Okay, then Zoom is screwing up on me because it only shows 2 people.
I'm still here.
I am as well.
I see Tyler and I see Jocelyn, but I don't see the other 4 or the other 3 people.
I'm here, sir.
And you are, because your name's not, your picture isn't showing up. I mean, not even a blank screen for you. But there is a blank screen here, it just has no name. So the other 2 people are not there. Anyway, Zoom has been messing up for me all week. It's only the second day of the week. Okay. And so sine of pi over 4, again, is a square root of 2 over 2. Cosine of pi over 3 is 1/2 minus, and then the cosine of pi over 4 is square root of 2 over 2. And the sine is the square root of 3 over 2. We did this before, right? So that's going to give me the square root of 2 over 4 minus the square root of 6 over 4, which is square root of 2 minus the square root of 6 over 4. So that was a previous problem we solved. I had the same answer, but it was a different angle. And with sine and with the trig functions, you get multiple angles that have the same value. But they use 2 and 3. 3 minus 2 is 1. So they're using pi over 4, no, pi over 3 minus, no, pi over 4 minus pi over 6. Well, pi over 4 is the square root of 2 over 2. Pi over 6 is the square root of 3 over 2. Well, they got a sign. Wait a minute.
They use the wrong numbers.
This is interesting. No, that works out. Pi over 4, yeah. 3 pi over 4. 3 pi over 12 is 1/4. 3 over 4 is 1/12. 1/4, 3 over 12. And 2 over 12 is 1/6. It may have to do with the fact that I'm using a larger angle. I'm using larger angles to find that smaller angle. But I don't see why it would be different. I didn't think so. I'll have to explore that. So did I do something wrong? Because I said it was gonna be 4 pi over 12. Oh, that's 1/3. That's 1/3 minus 3 pi over 12, which is 1/4. So that changes things. Because now, oh, so that's switching these. So that's gonna be a 4, and that's gonna be, no, that's gonna be a 3, and that's gonna be a 4. So I'm switching the order of the multiplies.
But sir, where did they do that? Because they have pi over 4 and pi over 6.
Because 3 pi over 12 reduces to pi over 4.
Yeah, I see that in yours. Okay, and then you have pi over 3.
Because I wrote it wrong.
Okay.
And that should be a 3 here. I mean, no, this should be a 3. And this should be a 4.
So it's still different.
Yeah, but they're still just one pi over 12 apart.
Okay.
And so the cosine, the sine of 60 is 1/2. And this is the square root of 2 over 2. No, the sine there is the square root of 3 over 2. And this is the sine, this is going to be a 4 here, and this is going to be a 3 here. So the sine of pi over 3 is 1/2. Okay. So I wrote these wrong. So they do equal the same thing. Get the square root of 6, the square root of 2 there. So we get the square root of 6 minus the square root of 2 over 4. Okay. That would be a -1 or 2 on the exam. Probably a -2 because reducing the fractions incorrectly. I'm picky about reducing fractions correctly. Which is why I get upset when I do it. Okay. So I have sine times cosine plus cosine times sine. So that means we're going to do 75 plus 15 degrees. And since it's sine, cosine, cosine, sine, that means it's going to be sine. Well, what's 75 plus 15? 90. So what is the sine of 90? 0. I just realized I had that.
I was wondering what that was, sir. The whole time I'm like, what's this thing in his ear? I don't want to be rude. You're jamming, sir.
I listen to stories. So I turned my story off, but I didn't take that out of my ear. So the formula of the expression is the right side of the formula of number 4. sine plus sine of alpha plus beta, with alpha being 75 and beta being 15. So that becomes what I had written there, which is a sine of 90, which is 1. And so that's kind of what I did here, recognizing that it was the sum formula for sine, where you're adding the two angles because of the plus sign here. Finding exact values. When you find exact values, that means you leave the square roots. Okay, so sine of alpha equals 1 over the square root of 2, which equals the square root of 2 over 2, with alpha being between pi over 2 and pi. That means we're in the second quadrant, where cosine would be negative. And then sine of alpha, sine of beta is a negative 1/3. So sine is negative in the third or fourth quadrant. So they're saying beta is between pi and 3 pi's over 2. So that's the third quadrant. Both sine and cosine are negative in that quadrant. So here we're going to use triangles to figure out those two angles. Okay. So since sine equals the square root of 2 over 2, then we're talking about a 45-degree angle. And cosine is going to have the same numbers, but since we're dealing in the third quadrant, second quadrant, cosine is going to be negative. So that means we have sine of alpha equals the square root of 2 over 2. That means the cosine of alpha is going to be a negative square root of 2 over 2. So I found two of the things we need to find. Well, one of them. And since sine equals a negative 1/3, and we're dealing with this quadrant, so that means I'm going to go down 1 unit, and the radius is 3. So we need to find this length here. And I added instead of subtracted because this is r, and this is y, and this is x.
1/2.
No.
Oh, well, the distance.
Use Pythagorean. No, it's not distance.
Oh,
This distance here is 3.
okay.
I want to find this distance. Because this point here is xy, the y value is -1. Because of which quadrant? And the x value is going to be negative as well. But the sign, I mean,
Yeah.
which
Is
angle we
it
talking
negative
about?
square root of 2 over 2 and?
Yeah.
For the x? Or for both, x and y?
Well, for alpha, which is this angle here.
That's positive.
Well, cosine's negative over here, but the sign is positive.
And both are gonna be negative down there.
Both are going to be negative down here. So this is the angle we're talking about.
Yeah.
So the reference angle, this is the reference angle. And so this is 1 here. What is this length here? We use Pythagorean theorem. Here I have the hypotenuse, here I have one side, what's the length of the other side? Well, 3 squared minus 1 squared, square rooted. So 3 squared
Two,
is,
one,
was 3 squared?
3 squared minus 1 squared,
Yeah.
2 squared.
Uh-uh.
Oh,
What's 3 squared?
oh, 9.
Yeah, 8. So you take the square root of 8. In your head, this should reside. Square root of 8 is 2 times the square root of 2. I factor out the square root of 4. So that's how I get the 2 to the outside. So the cosine of beta is, all right, we have the sine of beta is a negative 1/3, and the cosine of beta is also going to be negative. So it's going to be the square root of 2 over 3. I mean, 2 times the square root of 2 over 3. So there I have my essentials for doing these two things. I don't need to know what the angles are because I know what the cosine and sine of alpha and beta are by figuring it out by using the unit circle and or I think they use a triangle here on sine of alpha to find cosine of alpha. I just recognize that the square root of 2 over 2 is a 45-degree angle, sine or cosine. And the sign of it tells you which quadrants we're looking at. And so that's what they did here. So this side was 1 and this side was the square root of 2. And so 2 squared, square root of 2 squared minus 1 squared equals 1 squared. So this side here is 1 and it's negative because we're in the third quadrant. I square this, which is just 2. I square this and I subtract it from 2, which gives me 1. And then I take the square root of 1, which is 1. So cosine is this negative 1 over the square root of 2, which is the negative square root of 2 over 2, which is a 45-degree angle. This is 135 degrees, or 3 pi over 4. Okay. And so we find those. And then we find the other ones the same way. All right. Yeah, a lot of times I fall on this. Sine squared plus cosine squared equals 1. So I don't even need to know what do the right triangle. And I'll still get negative 2 squared. Well, I get square root of 2 over 2. And then since it's in the third quadrant, it needs to be negative. Because when you take the square root, you get a positive and negative. Okay. And they did the same thing here. And then they could also have done the cosine squared, sine squared plus cosine squared. But do they do that? Oh, yeah. So they end up doing the same thing. And sine was a negative 1/3, so negative 1/3 squared is 1/9, and 1 minus 1/9 is, 8/9, and the square root of 8/9 is 2 square roots of 2 over 3, and it needs to be negative. And then we'll start with, where are we? Over 5 minutes past, I'm sorry.
Are we? Oh.
Yes,
Oh, is that 2 hours?
Yeah, today's class went by kind of quick.
this class is an hour and 40 minutes long.
Oh.
All right, sir, I guess this is goodbye.
Yeah, till Thursday.
I guess this is good.
All right. See you next week.
Next week
Shit.
is Thursday.
I keep thinking today is Thursday. Sorry. See you Thursday.
Bye, everybody in class.
All
Bye.
right, bye. Call it the disembodied voice.
Yeah.